Hey everybody, now we're continuing our coverage of Chapter 7, which is for now, so far it's the Sn1 reaction. We'll talk about E1 and E2 as alternate reactions that are, some similarity. We ended on 5b, which was talking about the substrate and, different substrate effects. The substrate's the thing with the halogen on it, right, the leaving group. And the rationale for carbocation stability, because remember that we were talking about tertiary being the most stable carbocation, then secondary, and then primary and methyl are really unstable. And it's due to the kind of the neighboring effects of the CH bonds and the electron density in those CH bonds. So this was from last time. This is my kind of silly drawing of it. You can try making your own silly drawing of it, and the point being that each of the CHs and the pairs of electrons can stabilize the neighboring positive charge, right? It's because it's a carbocation. It's a carbon with a plus charge. And you have they have 9 of these, right? 3 on each of the different carbons. So there's 9 of these potential interactions. They're through space interactions, and the arrow here is, for me, is suggesting a through space interaction. So the little cloud of electrons, the 2 electrons here, can partially overlap the carbocation, the central positive charge thing. Okay, and that process we've seen before is called hyperconjugation, which we saw it when we talked about radicals, because it's the same explanation for why radicals are stabilized. Like tertiary radicals are more stable than secondary radicals, are more stabilized than primary radicals, which is more stabilized than methyl radical. Now, yeah, okay, so then I showed this also in my slides, and you can put these in your notes. We already talked about this, which was the energy profile for an Sn2 reaction versus an Sn1 reaction. That was last lecture, I think. And then, yeah, so if you look at like a methyl carbocation, it doesn't have any of these neighboring CH through space interactions, right? Because the H's don't do it. It's the neighboring carbon atoms. There's no neighboring carbon atoms on a methyl carbocation. But with like a butyl carbocation, you have all these neighboring interactions between the CHs, right? And those CHs cause a through space interaction, because this is a carbocation. Remember, that's a typo. That dot shouldn't be there. This is showing what a radical would look like, but indeed it's a carbocation. So no dot, and there should be a plus charge. Okay. So yeah, and anyway, all these CHs do this, and it's a net stabilizing effect. This is a tertiary carbocation, and if you have a secondary carbocation, then it'll be a little less stabilization. If you have a primary, it'll be less than that, and if you have a methyl, it'll be less than that. The only carbocations that are sufficiently stable to exist are tertiary and secondary. The methyl and the primary don't exist, and we don't use those in mechanisms. They just don't occur. So methyl and primary do not occur. All right, so there's both of them again. Cool. And the other thing I'll mention is that this is the same explanation for why we observe radical stability. And like how tertiary radicals more stable than secondary radicals, more stable than primary, and then methyl. And in these cases, it's not a carbocation, right? A radical is not charged, but you do have a partially filled orbital, and so there's some vacancy for electron density. And that same thing happens with the hyperconjugation. With radicals, it's just it's a partially filled orbital. It has a radical. Okay. Okay, and then we're on 5b on the carbocation stability. Let's move to 5c now. And that is again, and we sort of talked about this, so I'm just going to mention it one more time. If you have a secondary alkyl halide, or thing with a leaving group, that's the gray area, right? Because it could either go Sn2 or Sn1. Sn2 versus Sn1. Let's mention that one more time, just to make it very clear. When do you kind of expect an Sn2 reaction, and when do you kind of expect an Sn1 reaction? For Sn2, the main things are a polar aprotic solvent would help. Polar aprotic solvent, DMF, DMSO, acetone, etc. And typically you need a good nucleophile. And that's kind of that's explained even by the kinetics, right? The nucleophile is part of the rate equation, so having a good nucleophile is kind of critical for an Sn2 reaction. All right. Now for an Sn1 reaction, polar protic solvents seem to be, polar protic solvents seem to stabilize the departure of the leaving group better. So that's like methanol, water, water, methanol, alcohols, etc. And then the nature of the nucleophile is less important. Nature of the nuke, less important. So you can get away with a bad nucleophile, and the bad nucleophiles are often the solvent. So often the solvent helps dissociate the leaving group, and then the solvent also acts as the nucleophile, right? So water acts as nucleophile, methanol or ethanol acts as nucleophile. Okay. And so like Sorbolysis, which is the example of using a solvent to dissolve the material and also to act as nucleophile. The Sorbolysis reactions are okay with a terrible nucleophile. Sorbolysis reactions are okay with a terrible nucleophile. Okay. So let's show a couple examples just to sink that in. And Sn2 versus Sn1. We already showed examples of this, but it doesn't hurt to show a couple more. Remember, this is one of the weird leaving groups. It's a non-halogen leaving group. It's called triflate, or TFO, because the oxygen, TF does not refer to this oxygen. The TF refers to the S double bondo CF3. So TFO refers to the overall thing, and it's called triflate. And it's a leaving group. Okay, so if I have this chiral secondary molecule with a triflate, and I react it with water, is this going to be an Sn2 reaction or an Sn1 reaction? Remember that water is a terrible nucleophile. And it's also a solvent, it's a polar protic solvent. All of those kind of add up, and you're like, okay, well that's probably going to be an Sn1 reaction. And remember, since an Sn1 reaction goes through a carbocation, you lose the chirality and it becomes a racemic mixture. I'm not going to do the full mechanism, but I'll do the first step, which is dissociation of the leaving group. Of course, you get a carbocation, and then a couple more steps to make those two products, right? Nucleophilic attack, deprotonation, and that's the Sn1 reaction in a nutshell. Nice example of Sorbolysis, and yes, you can use a triflate, but what if I take that same triflate, I'll abbreviate it this time, it's the same exact molecule, and just say OTF. And what if I maybe treat that with a good nucleophile and maybe a little bit of acetone as my solvent? Then I see the good nucleophile, I see the acetone. Good nuke. Why is it a good nucleophile? It's negatively charged. Put brackets on the carbocation. It's negatively charged, and that works really well for the Sn2 reaction, where we're attacking a delta positive carbon. So yeah, the mechanism is super easy. Attack, kick off, and what's the product look like? It looks like the starting material, but instead of a triflate, now the sulfur is attached. A couple students were asking me about well, like the connectivity of the product, I guess, and they drew some weird connectivity, and I guess my point is that that I'm trying to make is that the mechanism tells you what the product's going to look like, right? We're creating a bond between the sulfur and the carbon, right? Now I will draw the sulfur on the bottom, but yeah, it's 4 carbons here, then the sulfur is connected, and then you have 3 carbons on the sulfur, right? And what's the stereochemistry going to be? S. Something like that. Okay, there's a sulfide. So yeah, if you're confused about the connectivity of the product, look at your arrows, particularly the first arrow, which makes the bond. Okay. All right, and this is an Sn2 reaction, and the top was an Sn1 reaction. Cool. All right. In both cases, the leaving group is triflate, and I'll just draw the leaving group. Is when it falls off is S double bond O double bond O. Whoops. CF3. Right? And why is this such a good leaving group and a nice happy thing to fall off? It's because it has extensive resonance stabilization. Right? Resonance, etc. Okay, cool. So yeah, that's the structure of the leaving group, is the triflate ion. 2 more real quick. Okay, so we have a tertiary bromide. I'm using ethanol as a solvent. What do you think? Sn2 or Sn1? Obviously Sn2 is out of the question because it's a tertiary, right? So yeah, it's going to be Sn1, and now to show the product, it might help to do the mechanism, or at least a bit of it. Dissociate, attack, and then I flipped it around, it's okay. And then loss of the proton. So yeah, I flipped the structure around, it's not a big deal, everything's cool, the bonding is still correct. And yeah, something like that. That's an example of the Sn1 mechanism, right? But if I react with a tertiary bromide and maybe a good nucleophile, like we'll use the same one that we used above, and we use some acetone. And this is an Sn1 up top, Sn1, Sn2. Those are the Sn2 conditions. Good nucleophile acetone. Is it a reaction or not? It's a no reaction, and that's due to the fact that under Sn2 conditions with a good nucleophile and this polar aprotic solvent, it doesn't work because the back is blocked by everything, and tertiary substrates don't work in the Sn2 reaction. Okay. Alright, so for the time being, we're done with substitution and done with the Sn2 and the Sn1 reactions. We're going to move on to something called elimination reactions. Elimination reactions, and these are an alternative to substitution, but they provide a different functional group. They provide an alkene as a product. Alkene, what's an alkene? Remember what an alkene is? Alkenes are double bonds. So C double bond C. Elimination reactions are alternative substitution. They provide alkenes. And there's two mechanisms that we're going to learn. First we're going to talk about E1. And then we're going to talk about E2. Based on the number, and actually usually we don't subscript those. My bad. E1, E2, and based on the numbers, what do you think? Which one of these is unimolecular and which one of these is bimolecular? Well, E1 is unimolecular. And that's kind of the same, for the same reasoning that Sn1 is unimolecular. E2 is bimolecular. And they're going to happen in different situations, just like Sn2 and Sn1 happen in different situations. Alright? And I'll give you a hint. Just like Sn1 was a carbocation mechanism and Sn2 was not a carbocation mechanism, which one of these is the carbocation mechanism? The top one is the carbocation mechanism. And the bottom one is not a carbocation mechanism. Alright? So that's going to be a key difference right off the bat also. Alright. Alright, so let's talk now about unimolecular elimination, E1. Let's talk about unimolecular elimination, E1. So the main situation you should consider for unimolecular elimination, or E1 reaction, is that it's going to be a competitive reaction in Sorbolysis. So remember Sorbolysis, which is your Sn1 reaction? Sorbolysis reaction is typically Sn1. We've shown it to be exclusively Sn1, but it competes actually with E1. We didn't mention that because I was trying to just focus on Sn1. And E1 is going to be a minor product, so you don't see very much E1. You see mostly Sn1 product and maybe a little bit of E1. It might be like 80% Sn1, 20% E1. E1, okay? Alright, so example. Very simple Sorbolysis reaction. Methanol reacting with a tertiary bromide, and what's the Sorbolysis Sn1 product? Of course, I'm not going to do the mechanism except maybe show the carbocation, and of course methanol attacks and you get an ether, right? Methyl ether. And that's about 80% of the product mixture. 80%. Alright, so what's the other 20%? It's mostly going to be an alkene, which is kind of weird. We didn't talk about that before, but we were just introducing this stuff. Now we're telling you about elimination that also happens with Sorbolysis. Alright, let's show the mechanism of this all. I'll show how the elimination occurs. It's actually really not that difficult. So I'm going to repeat it again. Alright. Remember that the departure of the leaving group is actually kind of a slow thing. It's not really favored because you're making something that is not super happy. Although it is a tertiary carbocation, you know, relatively speaking, a tertiary carbocation is more stable than secondary or whatever, but it's really not a favored thing. And we actually saw this also in the energy diagram. Remember how we climbed in energy? We went to a little mountain, went over a mountain, and then we were in a little valley. The little valley is the carbocation, and that's why this first step is not favored. Okay, so yeah, Br minus, of course, is the leaving group, and then you make the carbocation. All right. Now, there's actually a couple things that can happen to the carbocation. I am going to draw the Sn1 reaction on the left and the elimination reaction on the right. And I'm not going to show the arrow for the substitution because we'll have too many arrows running around. We'll just draw what it makes and just envision, you know, what is the mechanism. You should know the mechanism, of course. I'll just do like a little mini arrow. Yeah, it attacks, right? I'm not going to draw that all the way to the carbocation because then it's going to get in the way of my other arrows. But yeah, of course, Sn1 reaction, I'll call attacks, and then you get, what do you get? Oh yeah, my solvent is methanol. Let's just draw that again, H3COH. Okay, and methanol. Alright, we're cool with that. That's the, and then there's a little, maybe a circle. Okay, yeah, the oxygen's positively charged. I'm not showing any stereochemistry, I just had to draw my lines better. Okay, and then what's the next step of the Sn1 reaction? I'm just going to say minus H plus. Of course, something's taking the proton off, right? The proton's got to go. That proton's got to go. It's either going to be methanol or Br minus. Maybe I'll draw methanol over here. H3COH. So, yeah, the proton goes away, right? Methanol takes it, or Br minus takes it. Somebody takes it. And then you make the final product, right? Let's draw the final product. Okay, Sn1. We know Sn1, so that's the Sn1 reaction. Alright. Sometimes we abbreviate this, like a deprotonation, a simple loss of a proton, as minus H plus. A lot of times students really get annoyed when I do that because they want to say, where's the proton going? Who's taking it? Well, if you have a highly acidic proton and the pKa is like -3 or something like that for these, there's a lot of things that can take it off. And it's often solvent, it might be water or something. As we move along, like into organic 2, we're going to abbreviate this all the time because we don't care about little things like a deprotonation. Right now, though, you know, you're an organic 1 student. It's probably good to always show something, take it off. Okay. All right. So how do we form the alkene then? How do we form the alkene? And I explicitly didn't want to draw a long arrow here, just because my figure is going to get too complicated. But imagine another thing that can happen, which is rather than a nucleophile attack the carbocation, what's another thing that can happen? Methanol, rather than it being a nucleophile, like we showed here, what if methanol can be a base and actually take a proton off? Well, then it would just take the proton. And what do you get? You get an alkene. And what's the byproduct? It's protonated methanol. So H3C. and then you get something like that. Okay, so what are the two products of Sorbolysis? The ether, in this case it's an ether. Sometimes if you're using water as your nucleophile, then you get an alcohol out. But if you're using an alcohol as a nucleophile and solvent, you get an ether out, right? And then you get a little bit of an alkene. It's usually like 80%, 20% or something like that. I'm going to transition to PowerPoint for just a second. I'm going to mention the handout on E1 mechanism. I think it's figure 7.7 in the book. And it shows kind of like the orbital interactions and a little, you know, kind of what I just showed here, but in a little more of a computerized three-dimensional format. And also the transition state structure, the little double dagger thing, which is the structure of the transition state for the E1 mechanism. All right. So let's go see that. Alright, so this is our previous figure, the carbocation one. Let's move down a bit to the E1 reaction mechanism figure. Alright, so let's start on the left and then we'll move on to the right. So what do we got on the left? We got a nice carbocation. See that carbocation, see the little plus charge? Yep, it's a carbocation, and usually maybe Sn1 reaction occurs, or so a nucleophile attacks the carbocation position. But the alternative reaction for the E1 mechanism is something that's going to take the proton off the neighboring CH3. All right. And there's our methanol as an example. It's going to be used as a base rather than a nucleophile in this reaction. So how does that reaction actually occur? Well, it gets kind of close. The lone pair is pretty nearby to that hydrogen, and it decides I'm going to take that hydrogen. And so, of course, taking the hydrogen it's a process in itself that occurs through a transition state. So the transition state structure has the oxygen be partially bound to the hydrogen, and the hydrogen starts, the CH bond starts breaking, right? And as it starts breaking, where do the electrons go? Because there's two electrons there, right? Well, they're not going to go with the oxygen. They're not going to go with the proton. There's a pair of electrons there, and where are they going to go? Oh, look at this developing bond, the little dash, dash, dash. That is a double bond that starts to be developed. So in the transition state structure, which is, we have the little double dagger up top there, these things are reacting, and this also says rehybridizing. What does that mean? Because it was sp3, and in the very end product it's going to be sp2, alkene, right? So it's rehybridizing. In the transition state, it's kind of like halfway between sp3 and sp2. And then what happens at the very end? Oh, look at that. Now we have a nice alkene. The oxygen is happy with its proton that it took from the substrate. Now we call it protonated methanol because it is methanol with an extra proton. And oh, look at that. What do we have now? Well, that one proton's gone because the proton was lost. And now we actually have the alkene structure. We have a pair of electrons that make the single bond, and then we have a pair of electrons that make the second bond, the double bond. So this is a very cool little structure that shows the, how it can how E1 can happen from a carbocation. Okay. Okay, so we're still in the E1 reaction, which was number 7. Now we're going to talk about an interesting tidbit about E1 reactions, that they can give product mixtures. E1 reactions can give product mixtures. E1 reactions can give product mixtures. So as an example, let's show kind of simple Sorbolysis of this chloromethyl cyclohexane. Those aren't wedges or dashes or stereochemistry. I'm just showing just the bonds. I just darkened it because my pen's dying a little bit. And if we show the Sorbolysis of this, well, there are a couple different products. And the first one, you can envision the chlorine going away, water attacking, lose a proton, and that's the Sn1 product. So let's just draw the Sn1 product first. It's an alcohol, right? So as you know, if this goes away, water attacks, then it's protonated. You lose a proton and you get an alcohol, right? That's the Sn1 product. I'll call that A. A is the Sn1 product. All right. And interestingly, though, when you think about the E1 products, if envisioning that if you have a carbocation, let's draw the carbocation. The chlorine goes away. What do you got? A carbocation, right? Minus Cl. Minus Cl minus. So we lose Cl minus, okay? Now you have the carbocation. Well, if you think about elimination, E1 products, how many neighboring hydrogens are there next to the carbocation? Or different neighboring hydrogens are there on the neighboring, next to the carbocation? Well, we have something called well, I'll call this one HA, and we have HB, right? We also have another one on the other side, but that's analogous to HB. So if, you know, there's one there, there's one there. Those will give you the same alkene. Okay. So if I remove HA, I make one alkene. What's that alkene look like? So, because remember, that's all the elimination reaction is. E1 is you take off a neighboring proton and it forms an alkene, right? So what kind of alkene? What's the structure of the alkene? And I'll call that B over here for the product B. What's product B? Assuming HA gets removed. And my A and B here are different than the A, B, and C that I'm going to have up here. So just don't worry about that. All right. So yeah, maybe I can have. Reorganize my paper a bit. All right. I can have that, right? That'll be an E1 product. What if that proton gets removed? Well, that would make another alkene. That would look like that. And I'm just going to call that C, even though I have A and B here. This is A, B, and C here. So see how that happened? Okay. So what I'm going to do, just to be clear on the mechanism, I'm going to redraw this 3 times and then just show how this all happens. It's just the mechanism, just to as you guys are learning this stuff. So we got plus charge, water attacks, and then of course there's a second step, minus H plus. Water attacks, and then you get it attached with a plus charge, and you have to lose that extra proton, so that's minus H plus. Final product is the alcohol. Remember, this is actually always the major product too. Major. The elimination products are minor. Okay, But let's just show now the mechanism of how these other two elimination products happen. And to do that, I'm just going to recopy my carbocation. And maybe I'll put my little H up there. This is what we're calling HA or whatever. And water takes it, H2O. Takes the proton. That's how elimination occurs. It just takes the proton and makes the alkene, right? How does the third product form? Where's my carbocation? I switched from blue to black there. And how could we possibly form that alkene using this carbocation? Now we're showing this proton. How could you possibly form that? Well, it's pretty easy. You just do that. Cool. So that shows kind of like three mechanisms of how we form these three different products. And the Sn1 is the major. These two ones are the minor. Alright. So yeah, that's pretty cool. From this substrate, it actually does end up forming three products through two mechanisms. Sn1 or two different E1 reactions. Two different, and the only difference with the E1 reactions is ripping off different protons. Okay. Okay, so let's try a slightly more scary problem. In the spirit of Halloween, we'll try a slightly more scary problem. And let's see if we can figure out all the products for the sorbolysis of this reaction, this substrate. Oops. We'll use methanol for this one. Alright, so of course we'll get the Sn1 product, which is just chlorine goes away, oxygen attacks, lots of a proton. What's the functional group you create when methanol is the nucleophile in a sorbolysis reaction? You don't get an alcohol out because the alcohol gets consumed. You make an ether, so this will make an ether. But then the question is, how many elimination products are there going to be? How many elimination products are there going to be with this substrate? So, how many elimination products are there going to be? The answer to that is how many neighboring protons are there, different, unique neighboring protons, are there relative to that chlorine? How many neighboring unique neighboring protons are there? Well, I see there's two there, but you only count one of them, so get my blue out, and I'm going to call that, here I'm just going to call it B, because we're going to call the product A, the Sn1 product, okay? Okay, there's HB. Any more neighboring protons next to where the leaving group is? Because the leaving group is going to go away and leave a carbocation. Well, we'll call it B. Maybe up here we'll call it C. That's a neighboring proton next to where the carbocation will be. Any more? Well, we got that carbon, we got that carbon. Any more carbons next door? Oh, there's one. And I'm going to call this one HD. So we have B, C, and D. Okay. Alright, so total we're going to have four products. The Sn1, then we're going to have an E1, an E1, and an E1. Alright? So I'm going to draw each of those products first. Sn1 is really easy. It's just going to be the ether. OCH3 hanging off the middle carbon. maybe start with that. And then imagine the O from here, from ethanol, attached to that carbon. So that's a nice way to draw it. Okay, let's call that product A. What about product B? Well, B is going to have an alkene between those two carbons, right? Alkene, because this goes away and you get the alkene. So let's draw that over here. Where's the alkene again? It's between the HB and where the chlorine is, so it's going to be right there. Right, and I'll zoom out and you can see it. You'll be able to see it all in a second again. That's what I'm going to call product B. Notice that, yeah, that nothing weird about my alkene. That's a you can't have 5 bonds to carbon, and of course there's 4 bonds to that carbon. So, yeah, if you drew something with 5 bonds, you messed up. Okay. What about C? Product C. Well, in that one, it's going to be the alkene is going to be kind of up and down. So it's going to look like this, but start with the carbon skeleton structure, and then, okay, there we go. And that's C. Alright. I'm on the edge, so I'll draw D underneath. And then what's that going to look like? It's going to have an alkene between these two carbons, right? It's going to have an alkene between those two carbons. And I'll draw that down right here or something, I don't know. Okay, so start with the skeleton. And now that alkene is going to be going down. Whoops, no, my bad. It's going to be here. And that's going to be product D. Let's confirm that one more time. So I think it's between these two carbons, and of course you see that right there. That it's between those two carbons, between HD and where the chlorine is, and that corresponds to that product. Okay, good. And you know, just for mechanistic practice, maybe what I'll do is I'll draw the carbocation under each of these different products, and then just show like a mini mechanism or something. So for A, of course, what I'm going to do is maybe I'll just show the first step of the mechanism from here. Yeah, the chlorine goes away, right? Chlorine goes away. So what is it? What do we have here? Plus charge. And how do we convert the carbocation to the ether? I'm going to redraw my A a little bit over here. This is A. Methanol attacks. How does methanol attack that carbocation? Through the Sn1 mechanism. Like that. What does that give you? Now the methoxy group is kind of up here. Sorry, I drew this kind of small. Sorry about that. I'll make it work, but it's a little small. Okay, so when that attacks, when methanol attacks, then methanol is attached. But something's missing, right? What am I missing? When oxygen attacks and gives up its lone pair, then this is attached. And what's the charge of oxygen bound to 3 things? Plus, right? Okay, so that makes sense, right? Methanol attacks, then you have the protonated oxygen there. And then we do have that other step, and I can't really draw it just because I made the annoying mistake of drawing this too small. You can draw it larger on your page. But how do we lose the proton? Either the chloride takes off the proton or methanol takes off the proton. It's just a simple deprotonation. Due to my lack of space, I'm going to abbreviate that and say -H+. My bad in terms of drawing this too small. I can zoom in, see that? I got a zoom button. So -H+, so the proton gets lost, and then we get product A, right? So that's just the Sn1 mechanism. Okay, let's. These other ones are really easy though. So for product B, I'm going to assume the carbocation. With a proton right there. And a carbocation next door. And what did I call that? I called it HB, right? I call that HB, so let's call it HB here also. Alright, there's my HB. How do we form that the alkene from the carbocation? Very easily. It's just a loss of a proton. So, methanol. How does methanol react to make the alkene? What does it do? It just takes the proton. And the electrons go towards the carbocation, and then let's make the carbocation a little more prominent. Alright, and then that forms the double bond. That forms the alkene, product B. Okay, let's do it again for C. Alright, we got our plus charge, and that is what we're calling HC, so let's draw a little C there. How do we form the alkene using the E1 mechanism? Maybe I'll draw methanol, H3COH, H3COH, lone pair on oxygen, grabs the proton, forms the alkene, and that gives product C. Let's do D now. D's the same exact thing. So start with the skeletal structure, plus charge right. Whoops. Oh, I made a mistake that I'm going to correct. I just noticed it. I'm sorry. On D, there's a little problem with D. I'm sorry. My bad. And there's a carbon there on D, as you can see. They all have a carbon there. Carbon, 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 carbon now. And here's the carbon on the carbocation intermediate. Okay. So what I did is when I drew D, product D, I forgot to put that CH3 there, but I caught it, so everything's cool. Okay, so now we have the plus charge right there. Here's HD. How do I form the product? Draw methanol. Lone pair. Grab the proton. Form the alkene. And there's product D. Alright, so these are pretty easy reactions. Once you have a carbocation, either a nucleophile can attack, and that gives you an Sn1 reaction. This is all, a little bit of a complicated slide, but I stepped through it, so you should be able to reproduce this. We can either undergo Sn1, where the nucleophile attacks, or we can do these different E1 reactions where you rip off the neighboring proton towards the carbocation and make either one alkene, another alkene, or a third alkene. And those are all the same mechanism. Okay, and I already mentioned this, I'll just say it one more time. In this problem that we just did, there were 4 major products, right? A, B, C, and D. And here's the major one. We just kind of assume that Sn1 is the major. So, 4 products total. A, B, C, and D. A was Sn1, and we have the 3 E1 products. Sn1 is the major one. Okay. And one more tidbit. There is rationale for some of these, like, you know, if I consider B, C, and D, there are certain alkenes that are more stable than other alkenes. But that's actually the alkene chapter, and we're not going to talk about it right now. So for you guys, don't even, right now, don't worry about like, oh, is B better, or C better, or D better. That's something we'll talk about later when we get to the alkene chapter. All right? Or if you want to talk about it in office hours, I can give you a little preview of alkene stability and what makes some alkenes more stable than others. For now, though, you know, if you can figure out what the products are and say, oh yeah, well, there's an Sn1 product and a couple of E1 products, then you are good to go. One more little thing about the E1 reaction. For B, I was saying that there's different products. We showed, you know, that the E1 reaction can have different E1 products. The other thing about the E1 reaction that I should just mention, the E1 reaction typically occurs with weak bases. With weak bases. So, water or alcohols. Water or alcohols. For now, that's a pretty good general assumption, water or alcohols. And it's, you know, the other thing is that for now also, we just consider the E1 as just a byproduct of Sn1. Just consider that. There are definitely cases where E1 is the dominant reaction, but for now, E1 is just like a byproduct of Sn1 reaction. So just, you know, real quick example again. Water, okay, yeah, so Sn1 reaction. And then of course you would have a competing E1 reaction. So this is major, minor. Another one. Alright, so we have a tertiary iodide, terrible nucleophile, solvent. It's a Sorbolysis reaction. Both of these are Sorbolysis reactions, Sn1. And so you get these, whoops, I'm going to make my bonds really close to the oxygen. There we go. Sn1 and then maybe 2 different E1 products. And this is major. And these are the minor ones. Okay, so that's it for the E1 reaction. And these are weak bases. We'll talk about what happens with strong bases in a second, and that's going to be the E2 reaction. With strong bases, you get the E2. And what are the strong bases? I'll give you a preview. The typical ones are things like alkoxides, which we've actually seen a couple times, and sometimes they do Sn2, sometimes they do E2. We'll go through all that. And also like hydroxide, these negatively charged things with oxygen. Also this one, which is tert butoxide. It's tert butyl. Remember tert butyl? Tert butyl, 4 carbons. Everything's on 3 methyls on a carbon. All of these are kind of like these strong bases, and they're going to cause the E2 reaction, which is the next topic. Okay, so we'll give an introduction to the E2 reaction. E2 reaction. Is that unimolecular or bimolecular, you think? Unimolecular or bimolecular? It's bimolecular. That's what the 2 means. Bimolecular elimination, E2. So, intro. This is something that happens with an elimination reaction that occurs with strong bases. And we'll show what kind of strong bases cause this reaction. It's just a twist on the E1 reaction kind of that occurs with strong bases. So the typical strong bases we're going to see are going to be NaOMe, or we could call it NaOCH3. So Me is a methyl, right? CH3. So NaOMe or NaOCH3 or KOMe or KOCH3. Big thing is like sodium and then oxygen and then like 1 carbon. But NaOMe is cool, or K, potassium, whatever. The other one we're going to see a lot is the tert butyl version of that. So it's NaO tert butyl. Sodium methoxide or sodium tert butoxide. Both of these could have a K, right? So named out this, and I'm not going to test you on the names or anything. Sodium methoxide or sodium tert butoxide. Sodium tert butoxide. And I called these things, I gave them a name before. If it's like an alcohol but you have a metal on it, like a sodium, what did I call it? Remember? They're called alkoxides. Alkoxide bases. It's like an alcohol with a metal on the oxygen. It's like an alcohol but with a metal and oxygen. So like, of course, this is based on methanol, this is based on tert butyl alcohol. Tert butanol. Okay, but this is called sodium methoxide, sodium tert butoxide. Alright. And then we can contrast this with the E1. Because E1 does not use strong bases. They use weak bases. Remember that? What are the weak bases in the E1 reaction? The E1 reaction, those are always like an alcohol or water or something. It's the solvent you're using. Water, methanol, etc. Those are what we call weak bases. All right. Okay, given that, how do we know that these are strong bases and these are weak bases? How do we know? How? Is there a quantitative way we can know this? And we actually have a very easy quantitative way. How do we know? Base strength. It'd be cool if we had like a number, like a basicity number or something, but we don't really, organic chemists don't really use a number for basicity, but we do use a number for acidity. Remember the number for acidity? It's the pKa. So we use the pKa, which is the acidity number. But that's weird. How can we use an acidity number to measure basicity? And the key to do that is you have to look at the pKa of the conjugate acid. Look at the pKa, not of the base, because the base doesn't have a proton. The base is usually lacking a proton, right? Like these lack a proton on the oxygen. So you can't look at the pKa of these, right? But you can look at the pKa of the conjugate acid. So let's just consider a couple of these. Like what I'm claiming is a strong base, NaOMe. I say that's a strong base, and why do I say? And then we'll compare it with what I say is a weak base, like methanol. I say that's a weak base, strong base, weak base. So now we look at the conjugate acid. What's the conjugate acid look like? What's the conjugate acid of methoxide? It's methanol. What's the conjugate acid of methanol? It's a methoxonium. I'm not sure exactly the name of this one, but it's the protonated methanol. I don't know the name of it. Okay, conjugate acid. And then we look at the pKa of this protonated conjugate acid. And now, what's the pKa of methanol? You can look it up. I'll just tell you. You're not responsible to memorize pKa's, but methanol is roughly where water is. It's about 16 or so. And the pKa of this is about -2. That tells you this is around 16. That's not a -16. That's positive 16. This large number is a reflection on the basicity of this. Big numbers for the protonated conjugate acid say, that's going to be a strong base. Tiny numbers for the protonated conjugate acid suggest a weak base. Okay, so our conclusion is, our conclusion is that NaOMe is a strong base. And here our conclusion is methanol, or CH3OH, is a weak base. What is the cutoff between, what a strong base and a weak base is? I don't know. It's like something like 12 or 14. It kind of depends on the reaction. But certainly, for the E2 reaction, we want this to be around, 14, 15, 16 or so to cause good E2 reactions. And these are the bases for E1 reactions. Alright, so we're on the E2 reaction. And we're still on the intro section. I'm just going to show a quick example of it and show the rate equation. Then I have a little special topic that's going to be fun. So the intro, let's see. I'm going to show the mechanism. The mechanism of the E2 reaction. Alright, so let's just draw what a typical strong base. K plus O minus CH3. Alright, so it's KOMe, 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 K plus O minus CH3. And the product. What is and then this will make KCl byproduct and methanol as a byproduct. Let's put a parenthesis around those because those aren't really the point of the reaction. We more care about the main product, right? So, what is the mechanism? It's easier maybe than the E1 reaction because it's all a single step. Kind of like the way the Sn2 was a single step. Remember how Sn2 was a single step? All I'm going to do is use the base and do everything as a single step. That's how the E2 works. Just grab the proton, make an alkene and rip off the chloride. That's it. There's no mechanistic intermediates. There's no carbocations. In a way, this is kind of like the Sn2 reaction, which is a nucleophilic attack, right? All right. So the base takes the proton, makes an alkene, and kicks off the leaving group. How many arrows is that? 3. 1, 2, 3. So it's 3 arrows simultaneously, and that just gives you the product. You might say that's a very easy mechanism, and I would agree with you. Let's just show the rate real quick. So we did rates before. Rate K is the rate constant. There's two things, because it's to E2, right? It depends on, what do you think it depends on? The rate will depend on the constant, and it's the substrate and the base, just like the Sn2 kind of was. I'm just going to abbreviate the base as like L minus OMe, right? And it's moles per liter inverse seconds, right? It looks very similar to the Sn2 rate equation. So if I double the amount of substrate, what will happen to the rate of the reaction? Double that, it doubles the rate. What if I double the amount of base? It doubles the rate, right? So the rate depends on both of these things. It's a bimolecular rate. It's a bimolecular rate equation. And it depends on how many different quantities. So, 2, right? It depends on substrate and the base. And the base is the alkoxide, O minus OMe, alright? That's why it's an E2 reaction. Bimolecular elimination, alright? Okay, so we'll talk more about the E2 reaction next time. So, Halloween is right around the corner, and I thought I'd have a little Halloween treat for you guys and show you a reaction that might be an extra credit problem on the quiz. So if you pay attention, you might get a couple extra points. This is a reaction called Substitution Nucleophilic Aromatic, and it actually, I've taught this a couple times as part of Organic 1 as sort of just a fun Halloween thing, and so yeah, it might be an extra credit problem. I was actually going to dress like a pirate, but I forgot to do that today because I forgot that I was going to do this lecture. So this is a little bit of a pirate-themed organic chemistry reaction. I don't know if you've heard pirate jokes before. Sometimes we say, you know, what's the pirate's favorite vehicle? And you say a car, or what's the pirate's favorite musical instrument? You might say a guitar. Well, anyway, so what's the pirate's favorite chemical reaction? And if you look at this abbreviation, it's Substitution Nucleophilic Aromatic, and it's the abbreviation we use is SNAR. SNAR. It's kind of like an Sn2 reaction or something like that. This will be the magic word for any quiz problem that you might see on the upcoming quiz. SNAR, S-N-A-R. So Substitution Nucleophilic Aromatic, and that's going to be the magic word for our special Halloween treat. Okay, so what's this reaction? I'm just going to show the mechanism of it, and it's actually something that you should understand now as experts on Sn2 reactions and nucleophilic substitution, right? So if I have a benzene, this is going to be an aromatic nucleophilic substitution. So this will be a benzene. I'm going to draw the double bonds this way. So with a leaving group, it could be Br, chlorine, etc. That's the leaving group, right? And if I have a nitro group on this benzene, that's the nitro group, right? Nitro, we showed nitro before. And if I react this with a nucleophile, an interesting reaction occurs. And an interesting reaction occurs where the nucleophile replaces the leaving group. That may not seem too exciting to you, but it is. And the leaving group gets kicked off by the nucleophile. You know, for fun, I'm going to actually draw a real nucleophile. I'm going to draw S- isopropyl. Okay, there we go. Na+. And this is going to be S. There we go. Alright, so a real nucleophile. We know that's a good nucleophile. Okay. And leaving group could be bromine or chlorine or something like that. Okay, so you might say, well, that's just an SN2 reaction, right? The sulfur attacks the carbon, kicks off the leaving group. But it doesn't, because SN2 requires sp3, right? Like a tetrahedral carbon, and that's sp2. So this is not an SN2 reaction, and that's why it's the Halloween-themed SNR reaction, substitution nucleophilic aromatic. So what is the actual mechanism? All right. So, and this, you know, we'll actually learn about this in organic 2. It's a little preview of some of it there. The organic 2 material you're going to learn. The nucleophile actually attacks this carbon, kind of like you might imagine, and to kick off the leaving group. But it, rather than immediately kick off the leaving group, it actually pushes all the way down to the nitro. Like that. Isn't that crazy? It pushes all the way down. That it attacks, leaving group does not go away, and the nucleophile is just attached, and it goes pushes all the way down to the nitro, and then what do you got? You got your leaving group. What else do we have? Well, left bond didn't change, but the right bond's kind of shifted down, right? So now we got that there, and now we have a nitrogen. And what's on that nitrogen? We have an O- and an O-. We cool so far? And then we have a plus charge. And then where is that nucleophile? Oh, the nucleophile is attached up top, so we got sulfur, and there we go. And how do we get to the final product where the leaving group is gone? Lg-, chlorine, bromine, whatever. How do you think we go back to the final product? How do we finish this mechanism off? And then all we do is swing all the way back. So start with oxygen. Doesn't matter which oxygen you use, and swing it all the way back. Boom, 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 boom. Isn't that cool? And that is the SNR reaction, nucleophilic substitution aromatic. The only other fun historical tidbit is that this thing actually has a name. It's called the Meisenheimer Complex. I might misspell this. Meisenheimer Complex. You could probably Google it and get a better spelling, and it might even be a Wikipedia page. But this intermediate is a known characterized intermediate. Anyway, so this might be a small extra credit problem on the upcoming quiz, and don't forget the magic word of SNR. Happy Halloween, and if you go trick-or-treating, which hopefully you guys are all too old to trick-or-treat, make sure you be safe and wear a mask. Alright, see ya.